This is Brenda Wingard-Haynes, and this is Chem 207, and we are continuing on with Part 2 of Unit 1, which is the structure of the atom and periodic table and formation of ions, the octet rule, and D-block metals. In your last segment, we concluded with our rudimentary discussion of the atom, that atoms or elements are defined by the number of protons, and when we change the protons we get a new element. Our neutrons will add different mass. When we get different masses we get isotopes. When we change electrons we get a charged particle, and those are called ions. When we lose electrons we get a plus charge. When we gain electrons we get a negative charge. The positively charged particles are called cations, and the negatively charged particles are called anions. Now we're going to pick up with what the difference between mass number and atomic mass is. The mass number is unique to the atom. So this atom has a mass of 16, and this one has 35 and 23 and 24 and so forth. But remember, we can change mass by changing the neutrons and get an isotope. So the atomic mass is the weighted average of the isotopes that are found in the world around us. Now the question is, what is a weighted average? If we look at the periodic table, it gives us a bunch of information. It gives us the number of protons for sure, but you also see in your entries on the periodic table, for example, you might see carbon 6 and a number like 12.01. And so what that is telling you is this number that you see is an indication of the weighted average of the isotopes that are found in nature. And so since carbon has a 12.01, that tells you that even though, if you go back to 17, you have 1, 2, 3 different isotopes of carbon in the world around you, most of it has a mass of 12. That is the interpretation. So, your example of isotopes, again, carbon 12, carbon 13, carbon 14, those are 3 isotopes of carbon. Hydrogen 1, hydrogen 2, hydrogen 3, and so forth. And most elements in the world around us do have more than one isotope. So the question is, what does it mean to be a weighted average? Well, I like to start with a familiar example that most people can understand. Let's say you get the dreaded group project. The project receives 100 points. If there are 4 of you working on the project, how many points do each get? Okay, maybe I should change the word should. But nonetheless, this is what we call a straight average. And your straight average is 100 divided by 4, or 25. And so if you were going to use the model of the straight average, everybody would get 25 points. Now let's talk about the reality of working on a project. The project receives 100 points. In your group of 4, one of you does 50% of the work, the next 40%, 10%, and one of you does absolutely nothing. This is the quote-unquote fair world. So our weighted average would be something like this. There are 100 points available. The person who does 50%, okay, should get 50 points. The person who does 40% should get 40 points. The person who does 10% should get 10 points, and the slacker, no offense, but the slacker should get 0. Okay? So this is a familiar example of what a weighted average or distribution would show you. And at the end of the day, all the individual parts should add up to the total, which it does. So, determining atomic mass, or the value that you see on the periodic table, represents the weighted average, should be very similar. And this is probably new for some of you. We did not talk about this in Chem 110. So here are two examples. Nitrogen has two naturally occurring isotopes. One has a mass of 14.003 AMU and a natural abundance of 99.63%. So that right there tells you that most of the nitrogen that you see in the world around you has a mass of 14. And so you would expect your calculated answer then should be around 14 AMU. Okay, if it's not, you've done something wrong. However, there is a second isotope with a mass of 15.000 AMU and a natural abundance of 0.370%. Okay, so what we have to do is we have to calculate the relative abundance of both. Okay, so we have 14.003 times 0.9963. Here's the mass, here's the relative abundance in terms of a decimal, plus 15.000 times 0.0370. Put another 0 there. Okay? All right, so what we're going to see is that this component should be very small, and this component should be the bulk of your answer, and you would expect an answer of around 14 AMU. All right, so we need to make friends with our calculator. All right, so 14.003 times 0.9963 plus parentheses 15 times 0.0037 end parentheses equals 14.0066889 is what our calculator is showing us. Okay? Now, for significant figures, we should just not kill ourselves necessarily with this, but really, usually and typically, our significant figures will just say to round it to 4. 1, 2, 3, 4 gives us 14.01 AMU. And you think, well, that's an awful lot of work to figure out that answer. But basically, that coincides with what we predicted. Okay? Let's try another example.